KL divergence and duality. Most of our models will be maximum entropy models with constraints, but maximum likelihood is a really nice tool for working with data. KL divergence includes both as special cases. So we're going to start looking at probability distributions with weights or parameters. So each P in our probability vector, bold P, depends on some weight vector. This is called a parameterized model, and the weights are called parameters. Logistic regression, for example, we have a sample space with two outcomes, and we have this conditional probability that y is t1 given the observation of the x's and those weights. And the weights means that this is actually one component of a two-component probability model. It's the one for t1. For t0, we get p0 of w, which is 1 minus p1 of w, which looks like that. And p1 and p0 together constitute the probability vector p for two possible outcomes that we call logistic regression. So maximum entropy means we don't have to make assumptions about form. They're the best models in the sense of being maximally uncertain given the constraints. So our maximum entropy model is to find the argmax of the entropy subject to the constraints. There's the definition of entropy. We use a Gibbs form, which is an exponential form. The weights are in the phi sub i's that are in the exponents, and the sum of the exponential terms is called z, the partition function. But other than that, maximum entropy does not require explicit definition or some kind of exact specification of phi sub I of w. And this is very important because in data science and machine learning, we're often working with very complex multi-layer models. And we base our machine learning applications on architectures rather than on explicit forms. And we tend to optimize over the weights. So when we find P star as the argmax of the entropy, then the variables are these weights. The Gibbs form, again, means that our Lagrangian is negative of sum, that's the entropy term on the first, plus those are the constraints. And the solution satisfies that the derivative with respect to each weight w sub j in the weight vector of the Lagrangian has to be 0. We often use expected value constraints, which look like this. And that means we're looking at where this expected value summation is equal to b sub k. And let me explain. This f sub k is a function from the sample space to R, and it's a function of y, the variable. Notation here, we're saying f sub k of y, but actually we mean f sub k of t of y. We've done that many times now. So this is the expected value of f sub k of y, and with respect to the probability distribution p that we eventually are going to solve for. Now often the b sub k is the expected value with respect to another distribution, one that's given to us before the problem, and very often it's an empirical distribution, a distribution derived from the data. So in that case, the b sub k would be this exponential with respect to p tilde of these functions, and so our expected value constraints look like this. And our Lagrangian correspondingly looks like this. And we often rely on Gibbs forms and Lagrangians for the work that we do. Here's our Gibbs form. Take the logarithm on both sides, and notice we get the log of p sub y of w is phi sub y of w minus log z. So our Lagrangian is going to simplify to this form when we substitute in for the logarithm of p sub y, and we can separate the sum, and there's no y's in the log z, so we just get the sum of the probabilities, but that's equal to 1. And so we have this as our Lagrangian in terms of the Gibbs form. And we also get simple calculation that the partial P sub I with respect to W sub J is equal to this, which is P sub I times, in the parentheses, the partial phi sub I with respect to Wj minus 1 over Z, the partial of Z, the partition with respect to W sub J, component of the weight vector. But we seldom use the entropy directly. So we've got Y here associated with S, and we've got the probability distributions, pure entropy, cross entropy. We're going to use natural logarithms, so measuring information in nats. The KL divergence is defined to be the cross entropy minus the pure entropy. And that means that our maximum entropy models can take many forms. They're often expressed as likelihood models and just as often defined using KL divergence. So let's illustrate. This is our KL divergence. We proved a theorem saying it is non-negative, and it's equal to 0 when the P and the Q are the same distribution. So the KL divergence in terms of the logarithms looks like this. This is a convex combination of convex functions of P, which means that the KL divergence is convex in P, and we get a global minimum as a function of P. But likewise, the second derivative with respect to Q of that first term is positive, which means that we also again have convexity in Q and a global minimum as a function of Q. Let's look at what happens, for example, with the uniform distribution, where for R outcomes, the probability of any outcome is 1 over R. We know this maximizes the entropy. Let's see what happens when we substitute it into the KL divergence. So we get this, and properties of logarithms. 1 over R is just R, the negative one factors out and cancels with the negative one in the beginning. There's no y terms in the log 2 of R, so we can switch those two. The sum of the probabilities is 1. And so the KL divergence of P with respect to the uniform distribution is log base 2 of R minus the pure entropy. So if I want to find the argmax of the entropy, I could just as easily find the argmin of the KL divergence with respect to uniform distribution. In other words, it's the same P star for both. But what about for a Q other than the uniform distribution? So here we have such a Q, and notice I'm writing this Q in magenta so we can track what happens to it as we do our calculations. This is our definition of KL divergence. I'm going to do a little simplifying on the summation form and factor out the P sub y. And notice we've got a minus log Q sub y. That means that our Lagrangian for KL divergence minimization has a minus log Q in it. So I'm going to use a new Gibbs form, one that has the Q sub y in it. There are no W's in the Q sub y by assumption. So therefore I get this new Gibbs form. It turns out the derivative expression stays the same. And when I take the logarithm of P sub y, I get phi sub I of W plus log Q sub y minus log Z. And I've got a minus log Q sub y in the Lagrangian, so when I substitute, they cancel. Now, what I have looks an awful lot like the Lagrangian for entropy. So, in particular, notice that I've got mu sub k I used as the Lagrange multipliers for the KL divergence problem, and just because they're different problems, but I could let the mu sub k be equal to negative lambda sub k, and that would mean the following. If P star is in the set of probability distributions in R space, if the derivative with respect to W sub j, the jth component of the weight vector, of the KL divergence Lagrangian is 0 at P star, then the derivative with respect to W sub j of the Lagrangian for entropy at P star is also equal to 0. Now, convex functions have unique minima, so therefore the argmax of entropy is the argmin of the KL divergence. And we tend to call this Q sub y a prior distribution, and we tend to denote it using a P tilde of y instead of just the Q. Why? Because P tilde of y is often an empirical distribution. So KL divergence is often called the information projection of the distribution P onto the prior distribution P tilde. So we have a new maximum entropy model, which actually is minimizing the KL divergence in the first argument with respect to the constraints. And notice that it would reduce to the ordinary if we used uniform priors. And our solution is going to be in a different Gibbs form, a new Gibbs form that has this prior in it. But what about minimizing the KL divergence with respect to the second argument? Well, now we go back to our likelihood functions. So remember, a likelihood function is motivated by the joint probability of y1 being little y1 for trial 1 and y2 being little y2 for trial 2 and so on, which gave us this, because they're independent and identically distributed, it gave us this product form for the likelihood function. Zero probabilities do not produce trials, so we assume that S is just the set of all outcomes in the trials, and that would mean that none of these probabilities can be zero. So here's our likelihood function. We're going to make it a log likelihood function by taking the logarithm. And then using our exponent rule for logarithms, we can factor the m's to be coefficients of the logs. Write that in summation notation. So the natural log is an increasing function, so the argmax of likelihood is the same as the argmax of the log likelihood over the weights. And so we have what's called the maximum likelihood problem, maximize over the weights W, the natural log of the likelihood subject to the sum of the probabilities is 1. In other words, this problem. So our goal is probability models depending on these weight vectors. And our maximum likelihood problem is what we use to find them. Now, we're going to use a Gibbs form, the old Gibbs form, but notice that the sum of the P sub i's is 1, so we've already satisfied our constraint. And we can replace the log P sub I in the summation remaining, and we end up with this. And we're going to call that a function h, and we're going to take the derivative of h is set equals 0 because we're trying to maximize likelihood. Notice that for our derivative of the partition function, we have something that looks like this. The derivative of h with respect to a weight coefficient is equal to this sum minus m over z, the partial of z with respect to w sub k, because derivative logarithm. And notice that's going to be, when we distribute the sum, something looks like that. Notice we've got a 1 over z e to the phi sub I of w in the second summation, but that's just P sub I. So if we set the derivative of h equal to 0, we get that these two sums have to be the same. And notice I can divide by m, and I'll get the m sub I over m, but that's our empirical distribution. Now let's re-index in terms of y, just so it looks like what we saw earlier. And notice we can define functions from S to R by f sub k of y is the partial phi sub I with respect to w sub k. Substitute that in, and we have expected value constraints. So in other words, if we have our maximum likelihood problem, the solution satisfies expected value constraints. But notice that I can factor out an m and divide by an m inside the sum, and that's going to be my relative frequency, the counts over the number of trials. That's my empirical distribution. So now I have this, and I'm going to change this to minimization by putting a negative in front. But notice that I've got a negative sum of one probability distribution log the other probability distribution. That's cross entropy. So The maximum likelihood problem is a special case of minimizing cross entropy subject to the sum of the probabilities equals 1. Notice now that if this is our equivalent problem to maximum likelihood, that the KL divergence is defined this way, and therefore the cross entropy is the KL divergence plus the pure entropy, but the pure entropy of the prior distribution, which tends to be empirical. It's constant. We're given often the empirical distribution in an explicit form before the problem. So that means that finding the argmin of the cross entropy is the same as finding the argmin of the KL divergence in the second term. So here's our equivalent problem. Minimize the KL divergence of the empirical distribution with respect to P in the second term subject to our sum of the probabilities is 1. In other words, maximizing likelihood is the same as minimizing KL divergence over the second argument, but maximizing entropy is the same as minimizing KL divergence over the first argument. Now, KL divergence of P tilde with respect to P is not the same in general as the KL divergence of P with respect to P tilde. However, notice that we have this problem, our maximum likelihood problem equivalent to it, and this maximum entropy problem, and we get the first problem satisfies the expected value constraints, and so therefore if the constraints for the maximum entropy problem are these expected value constraints, what does that mean? We get the same argmin distribution for both. In other words, we have the best of both worlds. The maxent models use constraints rather than explicit definitions, no assumed models, but likelihood is flexible and very pragmatic. For example, we often write likelihood as a sum over individual trials. How do we do that? Well, first we need a definition of what's known as an indicator function. So if A is a subset of our sample space, then 1 sub A of S is a function, or a function from S to 0, 1, and it's just the characteristic function of A. It's 1 if X is in A, and it's 0 if X is not in A. So notice the sum on the left, we can write it as the double sum on the right. Why can we do that? Well, because the indicator function of T sub j is 1 exactly M sub j times in the M trials. Let me illustrate with an example. So here I have some trials, and my sample space is T1, T2, T3, T4. Here are counts, color-coded to make it easy to see the counts. I can write the summation in either way, addition's commutative, but notice using the second form, I can take the I equals 1 to 10 of the indicator function, T sub j y sub I, isolate that with some parentheses, but notice that the 1 T sub j is going to be 1 exactly M sub j times as I run through the y sub i's. In other words, I get M sub j. So I can write this in expanded form, looks something like that. And notice I've got all these indicator functions, but for each I, only one of those indicator function terms is non-zero. So for example, I get log of P2 when I is equal to 1 because the first trial was T2. So the other indicator functions were 0, leaving only the P2 term. The second trial was T4, and that meant it left only the P4 term, so on and so forth. In other words, this is a likelihood representation, or representing likelihood per trial in this notation. So let's look, for example, at logistic regression. We have M independent trials whose outcomes are little y1 to little ym, and our sample space here is just two possibilities, T0, T1. And these trials are conditioned upon features. In other words, we at trial y1 we observe features x1, and at trial ym we observe features xm. Our goal is a probability distribution which will consist of two probability coefficients, a p0 and a p1, that are functions of x and w. And this is going to be a maxent model of the conditional probability that y is t sub j given that x is xi. So here's our definition of conditional probability. And you'll notice we've got this probability that x is xi on the bottom. That comes from the data. It's just an empirical probability. So we can rewrite this as m over ki, where ki is the number of data points where x takes on the value xi in m trials.
Our Gibbs form is for T1 is the P1, looks like this. The Z is the denominator. We can simplify by multiplying by e to the negative phi1 xw over e to the negative phi1 xw. And we can write that ultimately in this form where k of xw is this phi1 minus phi0. Notice I could have gotten the same model by simply saying phi1 equals 0 and k of xw is negative phi0 of xw. And this k of xw is called a kernel function. In classical logistic regression, it's w naught, the intercept term, plus w transpose x. So here we have our Gibbs form in terms of the kernel for T1, probability that y is T1. And here we have it for T0. Classically, that would look like this. So what we're going to do now is we're going to, instead of use T0 and T1, we're just going to say our sample space is 0 and 1. And the advantage there is it makes it easy to define our indicator functions. For example, if y sub I is either the 0 or the 1, then the indicator function of y sub I is just y sub I. Whereas the indicator function of y sub I for the 0 possibility, the 0 outcome, is 1 minus y. If y sub I is 0, the indicator function should be 1, and 1 minus 0 is 1. Whereas if y sub I is 1, then the indicator of 0 for 1 should be 0, and we get 1 minus 1 is 0. So our cross entropy is going to be uniform prior, so that's the independent trials. And it looks like this. And we can write out our indicator forms, and now we can put in our indicator definitions. And notice lastly that P0 plus P1 adds up to 1, so therefore P0 is 1 minus P1. And so here we have our final form for our cross entropy. So here is our cross entropy, binary cross entropy, because there's only two outcomes, 0 and 1. Inside the sum is what's called the binary cross entropy loss. We'll be calculating this when we use our stochastic gradient descent, and then the actual cross entropy summation of all those will be an expected value. So let's notice that we could substitute the Gibbs forms, which would look like that. And notice that we have in the second term the natural log of e to the k of xi comma w. So I'm going to take that logarithm and put it out front. And notice that's going to leave me with 1 minus y plus y as coefficients of this log of 1 over e to the k xi w plus 1. And we have a negative 1 over m out front. So when I bring that through into two sums, it will look like this. And I use the property of the logarithm to cancel the negative that came in and get a plus there. So here is my Lagrangian, and I take its derivative with respect to w sub k and set it equal to 0. And notice that I have in the first sum 1 over m, and then the sum of the y sub I is the partial of k with respect to w sub k. The second one, 1 over m, I equals 1 to m, of the probability. Because when we took the derivative of the logarithm, we actually ended up with the probability P1. Now let's look at this for our classical kernel, classical logistic regression. Then we have the partials are xik when k is not 0, and when little k is equal to 0, we just get the derivative of x0 is 1. Here were our equations from the previous slide. Substituting, we end up with the partials becoming the xiks, and then for the w0 term, we get this expression. Notice we have an I equals 1 to m of y sub I. Y sub I is equal to 0 or 1, and it's equal to 1 exactly m1 times. So that is our empirical distribution. And the first thing is an expected value of the empirical distribution is equal to the expected value with respect to p of our features x. And these are what are known as the balance equations of classical logistic regression. Well, we're going to need a lot more. You see, the balance equations actually says that classical logistic regression largely ignores the data. The observations play a very limited role because we're going to get relatively little information because the balance equation says everything's dominated by the empirical distribution from the data itself. The x sub I is, the conditioning on the x sub I doesn't really do that much. So we're going to need more kernels with properties that can help us extract more information and more control over the coefficients so we can tune them to make better quality predictions.